Good morning or afternoon, year 13. We are today carrying on in our booklet. This is the second lesson on regression, correlation and hypothesis testing. So lesson 1 covered all of the work from book 1 chapter 4. There's a video if you need it. So we're starting from here. So today we're moving into S2 chapter 1. Now since it was, before half term that we looked at that, we're going to start off today with a recap of what we learnt last lesson. So first of all, we're going to check our vocabulary. So we know what correlation is. It's how closely two variables are linked. It can be positive correlation, it can be negative correlation, or it can be no correlation. Remember, correlation does not mean that one variable causes the other to change. So correlation doesn't necessarily indicate causation. We've got the things on the x-axis. So we call that the explanatory variable. And then the thing on the y-axis would be the response variable. Okay. Or another way of talking about those is the independent on the x versus the dependent on the y. So x is what we control, the thing we put in, and y is what we get out, the thing we think is being affected. Now, linear regression. A regression line is what we used to call a line of best fit, lower down in the school. Okay. And the regression line, straight line y equals mx plus c. Instead of doing it like that, instead of m, we use b for the gradients, and we write it the other way around. So y equals mx plus c is a straight line. For a regression line, we call it a plus bx. So that corresponds to the y-intercept, and that corresponds to the gradient. Okay. Now, little something here, the regression line of y on x part means x is the explanatory variable. That's what we'd expect, and y is the response variable. A positive b, so a positive gradient, would indicate positive correlation, and a negative gradient would indicate negative correlation. So this is what we already know from book 1. So we're going to nip through this question first. The data shows the number of shots, x, okay, so that one's the explanatory variable, and the number of goals scored. So x is what we control, y is as a result of it. By a football team over a number of matches. So when there were 15 shots, 2 goals were scored. There were 12 shots, 1 goal was scored. So identify the explanatory and the response variable. So that one's the explanatory, and that one's the response, okay, which we'd expect because they're x's and they're y's. Calculate the regression line of y on x. Now, I can't remember whether we did this directly in the last lesson, but I'm just going to run through as if we hadn't, okay? So what I want you to do here is go to your calculator, and you're going to go to menu 6, where you've got the stats menu. And I want you to press there, option 2, which is y equals a plus bx. Sorry, I'm trying to press and write at the same time. And you'll see that you can enter in your x values and your y values. So enter those in, and it's quickest to go down the x's first. 15 equals, 18 equals, 19 equals. And when you get to the end, press your up button and it will take you back up to the beginning of the list. Okay. Now, when I have done that, I then press option, and then you want 3, which is 2 variable calculations. So option 3, and it will bring out 3 values for you. So you'll get your A, which is minus that to 3 significant figures. You should be doing this. You'll get your B, which is 0.204. And you'll get your R value. I tend to just write them all down, just in case I come out of that menu and I don't want to type them down. And at the top, it does say at the top of that screen, y equals a plus bx. Okay, so that is there for you to remind you that that's the regression line. So for part B, the regression line is y equals a plus bx. So pop those in, okay? So minus, yeah, that's fine. And note here that it's got a positive correlation, it's got a positive gradient. And when you check your correlation coefficient, which is R, can't remember if I've taught you that, but we'll do it this time anyway. So your correlation coefficient is R, that's your value between between -1 and +1. So this has got a really nice strong correlation, okay? In the next, so part C, describe the correlation shown. So you can use your R value there, or you can use your gradient, so it's positive. And it is strong positive correlation. In the next match, the team had 5 shots. Use your regression equation, so use this that we found in part B, to estimate the number of goals scored by the team. So for D, we're going to substitute in x equals 5. And that will give me this value here. Now that tells me that if we have 5 shots, according to our model, 5 shots is going to bring out minus 0.06 goals. Well, it has struggled to bring out minus anything goals, okay? So therefore it's an unreliable model at that stage. And if you look at all your values of x that you have used within this to build your model, the lowest value is 7. So x equals 5 is outside the range of the data. So you'd write something like, it is outside the range of the data. So we would be extrapolating, which is unreliable. Okay. Right. So now we're going to look at finding regression lines with coded data. And we talked about coded data in book 1. So coded data has been transformed by some function to make the data easier to work with. You can find a regression line for coded data, then transform it into a regression line for the original data. So in this question, we've got these numbers, which are, to be honest, we're going to use our calculator. So it probably isn't that much of a hardship to just use the original data, but we have to learn how to do it with coded data. So this is the annual heating bill, H, so that's the heating bill in pounds, okay, for 8 different office buildings, along with the total floor area in metres squared. Okay, so the thing we control is the floor area, the response variable is the heating bill. And then the data is coded. So first of all, we find a new variable U by subtracting 2,500 from F and dividing by 100. We've got a couple that we need to fill in on this table down here. So the third one along. So that one is 1,500, then take away 2,500 and divide by 100, and we get minus 10. So I'll put that missing one on. And the other one that's missing is this one here. So again, subtract 2,500 and divide by 100, and we get 9. And then the code for the second variable, so we're no longer using H, we're going to code it by taking off 4,000 and dividing by 100. So we do that with the missing values down here, and we get those values. Okay, so we've completed the table of coded data. Find the regression line of V on U. So we're going to put these into calculator. And you want to find, again, I always write out A, I write out B, and I write out R, and then write out your regression line. Okay, so if you pause the video, you should be able to do that now. Right, when you do that, if you've got it right, A is 0, B is 1.036, and R is 0.979. So our regression line becomes V equals 1.036x. And I've just written Y and X because I'm programmed. Okay, so X is U, Y is B. Okay, so we get that. So that's the regression line of V on U. So it's a regression line for this data here. Now we want to now transform it back for part 3 to find the regression line of H on F. So what do we know about how H and F are linked? Okay, well, we know V equals 1.036U, and we know that V is equal to H minus 4,000 over 100, and we know U is equal to F minus 2,500 over 100. So we're going to sub those in. So that gives us this. Okay, and then we want to tidy this up. So firstly, I can see that both sides are being divided by 100, so they'll cancel. Then I'm going to expand the bracket. That value is 2590. Okay, and then I want it to read H equals. So bring the 4000 over here. And in fact, we normally put the constant first, don't we? When we're writing a regression line. So 1410 plus 1.036F. Okay, so that's one thing you have to be able to do. So code your data, find its regression line, sub back in to find the regression line of the original data. Okay, right, that is good. Now, I want to just talk a little bit more about the regression line. I've written you some brief notes here. So I'll just pop onto this screen here. Right, so what is regression? This is what we've looked at so far, straight line regression lines. So for example, time spent revising and the exam mark. So this regression line gives us a model for this data. So we've come up with a model to explain the data. And in this case, it looked like the points kind of lay in a line. So we used a linear model, okay? Whereas sometimes, like take this example, this is how rabbit population changes over time. Now, this increases exponentially, okay? It's a curve. So for some variables, like population with time, it might be more appropriate to use an exponential equation. For example, y equals ab to the x. And then you'd need to find out what a and what b and what x are to match the data. So it's almost like a regression curve. It's not called a regression curve. Okay. So let's see how we do that. So this is just an example of a curve. Y equals something times something to the power of x, where a and b are constants, will be a curve. So let's take that curve. I'll do this again in a minute on the other notes so you can have a look at it. But take the curve and let's transform it into a straight line. So we do that by taking logs. So log one side equals log the other side. Split this one up into log a plus log b to the x, and then bring the x down. And what you're left with is this. Now, if a and b are constants, log a and log b are constants, okay? And this is in the format of a straight line. Something equals something plus gradient times constant. So I've written underneath big Y equals A plus BX. So if I plotted, instead of X against Y, which we know brings out a curve, if instead I plotted the thing that's in place of of y is log y. So if I plot, I think I've put it here. Yeah. If I plot x against log y, it will bring a straight line. And that straight line will have gradient log b and intercept log a. Okay. So I'll do that again because in fact there's two different types of curves that we're going to need to look at. So I'll do that one that I just did. I can't remember which one it was. Ax to the n. Let me just check. Ab to the x. Yeah, just different numbers. Okay. Let's use this one. So this is the one we just did. So let's just do it a little bit more slowly. So y equals kb to the x. Just remember what those things are. This would be x plotted against y, which we say is going to bring out a curve, and we want to transform it into a straight line. So it's like another coding, okay? So we are going to take logs. So log y equals log kb to the x. And then we're going to split it in the second one. So log y equals log k plus log b to the x. And then you're going to bring x down, bring power down. You get log y equals log k plus x log b. Now we've got something, I'm just going to write over this in a nice light colour, that reads y equals a plus b x. Okay, I'll write that again underneath now. So y equals a constant plus b times x. So the thing that would have to be plotted in order to use this straight line would be still x, because that's still x, against log y. So that is what you would have to plot. We're not actually going to plot it. And when you do that, you would get a line with gradient log b and intercept log k. I know that because there's my gradient and there's my intercept. Okay? This will all come together, don't worry. I'm just going to move that along. Right, this is another curve. It's different. Look, in this one, the power was x. So that's a type of curve. This is a different type of curve. X is being raised to some power. Let's do the same thing again. Let's take logs. We get log y equals log a x to the n. I'm going to split the second one. Log y equals log a plus log x to the n. You're going to bring the n down, bring the power down. You get log y equals log a plus n log x. Now then, this is now in the form y equals a plus b x, where you're plotting not x against log y this time, but log x against log y. So here's log x and here's log y. That's what would be plotted. It would bring out a straight line with gradient n and y-intercept log a. So that's from there and that's from there. So we're not going to learn rules according to what type of curve it is. We're going to take logs each time. Now let's see how it feeds into these types of questions. So a student, a student records the height of 5 plants and the amount of fertiliser each plant was given. Okay, so explanatory variable and then response variable. The relationship can be modelled with h equals a f to the b. Okay, so f and h are our variables. A and b are our constants. Use the data to find values of a and b to 3 decimal places. Okay, let's start by taking the equation of the line. So h equals a f to the b. We're going to take logs. Log h equals log a f to the b. We're going to split log a plus, I'm just going to bring the power down as well because I'm too lazy to do it in 2 goes, b log f. It would be log a plus log f to the b, and I've brought the b down. Okay, so now we've got y equals a plus b x. So we would plot this against this if we were going to plot it. Log f against log h. So log f and log h would be the things that get plotted. All right, and what are we going to do? Right, I know what we're going to do. So we could, okay, I'm probably a little bit too lazy to do this, but what we'd really need to do now is fill in this table with log 12.3, log 13.1, log 20.5 and so on. But I'm going to put it all in my calculator. So I'm literally going to put it straight into the calculator. So when we go to menu 6, and then, can't find it again, menu 6, option 2, and then we enter our data in, you, instead of pressing 12.3, you're going to type in log 12.3. You're going to type in log 13.1. So I just go straight in the calculator with that, because if you work out each one individually and write them into this table, what's going to happen is you're going to get rounding errors. So shove them straight in the calculator, okay? When you do that and you do option and ask for two variable calculations, you're going to get your values for A, which is 2.6211, blah, blah. You're going to get your values for B, and I always write down my value for R in case it comes in handy in a minute, okay? And then we've got to write out what we actually asked for. Oh, find the values of A and B to 3 decimal places. Oh, okay. Right, so bearing in mind, don't get confused here, because this is what just came out of my calculator, okay? So coming out of my calculator gives me the gradient and the y-intercept. So I'm going to put those into this now. So it tells me log h equals 2.62115979. That is the thing in this position here, plus 0.1605 blah blah log f. So what they were asking for was, this is now equal to log A, and this bit is equal to B, and they want the values of A and B. So this is 10 to the power of 2.6211, blah, blah, because you assume this is log base 10 of A, so you undo the log, and that gives me 13.8 to 3 significant figures, and the value of B to 3 significant figures is 0.161. Don't have to do anything with that, because that is just B as it stands. A little bit complicated there, because the thing the calculator calls A is the y-intercept of our line, okay? So the answer isn't here, A is equal to 2.62. It's just our calculator calls that A, and our intercept is log A. So log A is equal to that, and then you've got to undo it. Example 4. Robert wants to make a rabbit population P with respect to time in T years. So rabbit population over time is going to be a curve. He proposes that the population can be modelled using the exponential model P equals KB to the T. So he would be plotting here. Where are we? Population against time, so T and P. The data is coded using x equals t and y equals log p. The regression line of y on x is found to be this. Determine the values of k and b. Right, this is always where I start. Take that and make it into a straight line. Okay, so log p equals log k b to the t. Log p equals log k plus t log b. Again, I've just done those two bits together, all right? Now, we're going to compare that with the line that he said he's got, y equals 2 plus 0.3 times x, okay? Now, take my highlighter so it's easy to do these comparisons together. So there's me plotting y against x, yeah? Because look, it's t against log p instead of p, so it's like the other type we looked at. So there is your y-intercept, and there is your gradient. And what we asked to find the values of k and b. So log k is equal to 2. So k is equal to 10 squared, so it's 100. And then log b is equal to 0.3. So B is 10 to the 0.3, which to three significant figures is actually 2.0. Okay? We didn't actually have to work with the data that time. We had to compare. Okay, example 5. So just change a little bit each time. If you always go with this idea, I always take the model and take logs and compare it to a straight line, and then normally the answer falls out. So the table shows some data collected on the temperature in a colony of bacteria and its growth rate. So original data plots T against G. The data is coded using the changes of variable x equals t, so the coded data will be x, and the y value, sorry, I should leave it as t, the x value is t, plots t against log g, okay? So it's sort of, if we look back at our two types, t against log g, it's that type. But again, I don't really like to learn the rules. I prefer to feel the question. The regression line is found to be this. Right, so Mika says, or Micah, the constant of this in the equation, in the regression line, means the colony is shrinking when the temperature is 0. Explain why Micah is wrong. So when t equals 0, so that's what we're asked for, when temperature is equal to 0, that would give me, look, these are equal to each other, x would be equal to 0, and y would be equal to minus, where are we? Here, sorry, from this equation line. So if x was equal to 0, y would be equal to minus 0.2215. So we know that y is equal to log g. And so log g is equal to minus 0.2215. So g is 10 to the minus 0.2215, which is 0.600 to three significant figures. So this is a positive value. Therefore, the colony is not shrinking. Yeah, if it's a positive, it would have a positive gradient. Okay, part B. Given the data can be modelled by an equation in the form G equals KB to the T, where K and B are constants, find the values of K and B. So back to the usual routine. Take logs. And you'll get that. I just took a few shortcuts, all right? Stick it against a straight line. Y equals A plus BX. So plotting log B against log, that's the wrong thing, B is a constant. Let's try that again, Thompson. So plus BX, okay? So plotting, I've just written the same thing again. B, oh, now it's the wrong pen. BX, let's try that. So plotting T against log G, which is what we said we would be plotting there. Okay, so T against log G gives gradient log B and gives y-intercept log K. So when we compare that with the equation that we're given, we get gradient of log B, so log B equals 0.0792. So B is 10 to the 0.0792, which is 1.2. So three significant figures. And then we're going to do the y-intercept. So log K is equal to that. We did it in the first part, didn't we? Yeah, we already did it up here. Log K. K equals 0.600 to three significant figures. Okay. Right. I think that needs some practice. So I don't think students find this particularly easy. It's a long time since you looked at that kind of log work. Okay. So exercise 1A, as much practice as you can, please. Rest of the